So go back to wonderful recording. And we really went through all of the parts that I wanted to touch on when it comes to the joys of our energy systems, but I want to come back to figure 2.12 and make sure that you guys understand this, okay? So we can see how we're getting each of these nutrients to move around the body accordingly. Now, the big question I have for you guys as we're looking through it, which is effectively when we're trying to produce energy for any physical activity that we're doing, okay? How are we able to increase the amount of energy that we can provide through anaerobic glycolysis? How can we actually be able to provide more energy inside of the individual muscle fibers through anaerobic glycolysis? What do we do? You can unmute yourself or go ahead and put it in the chat. No guesses? Can you guys not hear me? The question, Jordan, is how can we increase the amount of energy that we are creating through anaerobic glycolysis? What can we do to increase the amount of energy we're producing with that specific energy system acutely? What can we do to increase its ability? Now, glycogen is going to increase the amount that we can provide it for because we have a greater store of energy to come from. So that is one way to increase the total capacity, but I'm talking about the speed. So how much can we get right now? How can we get more energy from anaerobic glycolysis? Because if you understand this concept, guys, it applies to every single energy system, but it becomes important to understand the mechanism that's going to help us produce this energy faster. And thank you, Braden, for putting out an idea there. Come on, guys, somebody else give me something. Yes, we can increase the number of enzymes related to glycolysis. Great job, Zach. So with all of these energy systems, guys, the big thing to keep in mind is remember that rate-limiting enzyme. If we increase the number of those rate-limiting enzymes, we're going to literally be able to make that energy system go faster. So if we want to be able to utilize the ATP PCR system faster, so create more energy more rapidly, we're going to get more creatine kinase, CK, the enzyme that's important for that process. If we want to go ahead and increase the amount of energy we're going to produce through anaerobic glycolysis, we're going to increase all of the number of enzymes related to anaerobic glycolysis. Now, when it comes to our beta oxidation and our aerobic glycolysis, what can we increase the number of that will allow us to increase the energy production from those systems? Braden, great point. Oxygen is a limiting factor. So if we can increase the amount of capillaries and increase the amount of oxygen being delivered to each cell, we're going to be able to do a better job of using those aerobic systems. Absolutely. But what about inside the cell? What can we do? We can increase the number of mitochondria. Great job, Trendon. Guys, you don't have to answer in the chat like it's on Jeopardy and you have to always answer with a question. It's okay to take a shot. If you're wrong, you're wrong. Who cares? You guys are here to learn. So if we increase the number of mitochondria, well, inside of each mitochondria, that's where we're going to find all those enzymes specific to the citric acid cycle and the electron transport chain. Now, we can obviously increase that number inside of the individual mitochondria, but if we have more mitochondria, we effectively have more factories. And so that is also going to help with energy production. So now let's think about long-term effects from training. If you're doing a lot of aerobic work, anaerobic work, or otherwise, you're always going to get those enzymatic pathways for those energy systems you're using the most to upregulate. So you're going to increase the number of those enzymes, increase the amount of mitochondria inside of those cells, and increase the functionality of those mitochondria. Now, capillarization, so the amount of blood flow around it, is important, but it's very important that obviously we have those mitochondria, so we're going to be able to create that energy aerobically. Does that make sense to you guys? Go ahead and you put yes on the poll and participants, or no, and we can go ahead and talk through it more if you guys want to. Good. And remember, these energy systems are always specific to the muscle you're using them for, and then the actual muscle fiber inside of that muscle that you are in fact activating and utilizing. Good. So what you're going to find is that, like anything else, guys, the faster we're able to produce energy through these energy systems, the much shorter the availability is going to be. So we can obviously utilize all of these energy systems, and we're going to emphasize one over the other, but all of them are going to be working at the same time. The key is it's going to be the difference between, like right now, you guys just sitting, I imagine sitting, learning and listening, you guys are going to be utilizing predominantly beta oxidation with a little bit of carbohydrate oxidation, and then like less than 1% of glycolysis and ATP PCR. So we're always using all the systems. The key is which of them are we emphasizing? Now, as far as the application, we talked through it last time with the different sporting ideas and how different types of athletes are going to be emphasizing different types of energy systems when they're doing their training, when they're playing the sport, and it's going to be specific to the muscles they're using on the body. Now, is there any questions you guys have there about the application of that knowledge and why these energy systems matter? Okay. Since I'm not currently seeing anything coming up yet, but I know you guys might be typing something, go ahead again in the participants poll. Go ahead, either yes, we're going to go ahead and start chapter 3, or click no, and we're going to stay on chapter 2 and do a little bit more reviewing material. Thought I heard that. Yep, that's the door opening. How can I help you? That's all good. So, get after it. We're going to go ahead and move on to chapter 3. I'm in the classroom by myself. So when people come in, mask it or casket. So let's talk about the nervous system. Oh, Haley, click under participants and then go over, and then you should see like a yes or no option. I don't know if that, it might not work on cell phones, but if you're using it on your laptop or like, you know, kind of a tablet, bigger screen, you should be able to get to it. Now, the nervous system is arguably the most important system. If you don't have the nervous system, you can't even turn on the muscles. You're not going to be able to do anything other than just lay limp. So we start off with our central nervous system, brain, spinal cord. We then have our peripheral nervous system, sensory, so our touch receptors, our vision, our sense of smell, taste, our hearing, all those are afferent nerves. So that's giving information into our brain. It's also being processed through our peripheral nervous system. This is what gives us a reflex. Like if you accidentally touch a really hot stove, you'll pull your hand away before you even have the sensation of pain in your head yet. Motor efferent nerves is the ones where it's actually talking about contracting muscle, getting our bodies to move. Now that comes into two separate branches. We have our somatic side, which is the actual picking up and moving of objects by innervating our muscles. And then we have our autonomic nervous system, which is divided into two branches. We have our sympathetic nervous system and we have our parasympathetic nervous system. Our sympathetic nervous system is going to be our fight or flight. That's where it's time to get after it and do something. Whereas our parasympathetic nervous system is going to be our rest and digest. And that's what's going to be turned on when obviously we are relaxing. Specifically when you're sleeping, that's probably the highest parasympathetic tone you're going to get to. So our nervous system works upon a system of what's known as graded potentials, which can then lead to action potentials. So when we have depolarization, we're going to send that information on through an action potential, whereas we can have a slight depolarization and a hyperpolarization. So until we hit that threshold where what's known as the voltage gated channels open, we're not going to send the signal. This can be getting the muscle to contract. This is going to be having the sensation of pain, etc. Now, graded potentials can be both hyperpolarizing, so it makes it harder for the cell to depolarize, and depolarizing, so it gets us closer to that threshold. Action potential is just straight up excitatory. We're going down, no turning back. Now, these local changes are literally caused by the efflux, so that's going to be potassium going out of the cell, and influx of sodium into the cell. So inhibitory signals, potassium leaves the cell from the cytoplasm or sarcoplasm, depending on the cell we're talking about. And this is going to cause that millivoltage to move its way down, so it becomes hyperpolarized. Now, whenever sodium comes in, it's going to bring that millivoltage upwards, so that's what's known as depolarization. So once it hits a certain threshold, which for muscle is usually about negative 50 millivolts, for the actual, like your standard sitting around, you usually have about negative 70 millivolts. And so once we go ahead and get that action potential, it's going to go all the way down because it's going to open the voltage gated channels along the cellular membrane in a series going down the line until we get to the end where we're going to release a neurotransmitter, acetylcholine, where we're talking about obviously getting skeletal muscle to contract, and then it's going to go on to the next cell. So once again, at about negative 55 millivoltage, that's where we're going to hit our threshold. So if we don't get there, we're not going to have an action potential generated. If we do get there, we are going to have an action potential generated. And this gives us what's known as an all or none principle. So when it comes to our nervous system working, it's either going to completely fire or it's not going to fire at all. Okay. Now, once we go ahead and get to that threshold, now we're going to have a massive influx of sodium from that action potential. And once we get to that positive 30 millivolts, we're going to start to repolarize and actually technically hyperpolarize for a moment, where we're going to have the potassium leaving the cell along with we're going to be getting that sodium to go back to where it started. This is why your electrolytes are so important for muscle contraction, because literally this is what creates the electrochemical gradient that our body works upon. So what we have here is an example of how this is actually going to look if our x-axis is time and our y-axis is the millivoltage. So you can see once we hit that threshold, then boom, we take off. We have a massive influx of sodium. When we get to number 5, we close the sodium channels, and then we start opening the potassium channels, allowing potassium to go ahead and come back or go back out of the cell to bring ourselves back down. And then whenever we get further on down the line, we're going to keep getting more and more potassium back until eventually we're going to hit that hyperpolarization. So that's going to be the period between 7 and 8. And then eventually we're going to go back to where we're at our resting threshold. Any questions so far? Awesome. Thank you for hitting the poll button. Now, after we have that action potential, we are going to have what's known as a refractory period. Now, this is a period during which time it's either much harder to get an action potential generated again, or it's effectively impossible. The absolute refractory period is where it is effectively impossible. So no matter what you do, it's simply not going to happen because the tissues need to resensitize, they need to recover, and then be ready to go again. Relative is where if we send a big enough stimulus, we can, in fact, send another action potential. But this is where we're going to require a lot more incentive or a lot more signal. Does that make sense to you guys when it comes to refractory periods? Okay. So who wants to try to give us an example of what an absolute and relative refractory period would look like? Or something they can call upon from life to apply that? Car crash, maybe. Yeah, if you're in a coma, you can't really do much, but let's try not to go that dark. So, all right, let's go ahead and I'm going to pick on Tyler because it's fun and it's easy. All right, so to give you guys some context, whenever the cheerleading team competes, they do their nationals routine, which is effectively a 2.5-minute all-out exercise. Now, Tyler, obviously you've gone through this more than once. At the end of a full out, okay, how long is the absolute refractory period? Meaning it doesn't matter how much your coaches are yelling at you, there's no way in heck you're going to throw that routine again and anything's going to hit.
After the first time or after a couple times?
Either way, either way.
I would say probably after going full out one time, I probably needed a good solid 25, 30 minutes before I could go 100% in the routine the next time.
Okay, so that would be relative. That, as in you're ready to go, you could be forced into doing it. But I'm referring to like, how to say, you finish the full out and your coach is literally holding a gun to the head of a family member you care about, and you'd be like, they've had a good life. Would you say that is about a minute or two?
Yeah, I would say probably 5 minutes.
Okay. Does that make sense to you guys? As far as, you know, if you're thinking about sporting activity, giving it your best effort, it's like, hey, this is going to take some time. Thank you, Tyler. And so when we're looking at these refractory periods, obviously inside of the cell, it's far, far faster. So absolute refractory period, this could be something literally is only a number of milliseconds, but the relative refractory period might be something closer to half of a second. Now, In order to send the signal down our neurons, we use a fatty sheath known as myelin that's made by Schwann cells around those axons. Now, by utilizing what's known as saltatory conduction, where essentially the action potential is able to skip during the parts that are insulated, it allows things to go much faster. Now, I'm sure you guys have heard of MS before. That is literally a disease where the body naturally destroys its own myelination. Now, we can add myelination to speed up these signals. The other thing we can do is increase the diameter of our axons, in that if we have a bigger axon diameter, it is going to send that signal faster. So through myelination and increase axon diameter, we're able to send the signal even faster, which is going to get us a much more rapid contraction. Now, once we get to the end of that axon, we're going to, when it's coming to ending at the neuron and getting to our actual muscle cell, we have what's known as the neuromuscular junction. Now, this is where that action potential is going to cause the release of the neurotransmitter acetylcholine across the neuromuscular junction from essentially vesicles, which in turn are going to bind to receptors at what's known as the motor end plate. So that is going to be the ligand-gated receptor, where when that binds, or acetylcholine binds to it, it's going to open and allow sodium to start to influx. And once we have enough of this occur, we then have an action potential, which is going to cause the voltage-gated channels in neuromuscular junction open, and then across the plasma lemma, down in those T tubules, and then into our sarcoplastic reticulum, which is going to cause a release of calcium, which then leads to contraction. Now, there's a lot of different neurotransmitters in the body, okay? We effectively have two major categories where we have small, fast-acting and larger neuropeptides that are slow-acting. Acetylcholine and norepinephrine are some of the major contributors to exercise. Acetylcholine is the muscle contraction. It also is going to work through vagal tone in our parasympathetic nervous system to decrease our heart rate, along with norepinephrine is going to cause us to increase our focus and allow us to effectively work a little bit longer. It's very much like epinephrine, which we're going to get to in the next chapter when we talk about the hormones. Now, these graded potentials are going to be influencing whether or not we have a contraction or a lack of contraction. Through what's known as excitatory postsynaptic potential, if we're having these depolarizing effects, we're getting closer to that threshold, it's going to make it much, much more easily for an action potential to occur. And the opposite is true with inhibitory postsynaptic potential. So it's not a perfect example of this, folks, but how many of you guys have ever had that you're kind of woken up in a really deep sleep and it was physically hard to get moving? Like you just felt sluggish, you just felt like you couldn't really get moving for what you really wanted to do. That's an example of that inhibitory postsynaptic potential, and more or less just through the way that your nervous system works when you're sleeping, which is fascinating. Now, the other side of it is how many of you guys have ever had too many cups of coffee, or may or may not have borrowed some Adderall or something along those lines from a friend, and we're like, wow, I'm just really, really poppy and really fired up, and you know, you can't slow yourself down that well. That would be an example of something that's giving you more of that excitatory factor, so it's much more easy to do things. Nope, nobody else in here other than me has abused amphetamines at one point or another for fun? Okay, thank you guys. Thanks for not leaving me hanging. Now, we're going to start talking our way through. Too much pre-workout is a real thing. The dosage that some of these kids are doing, it's alarming, and it's also kind of entertaining. Now, we're going to talk about first the cerebrum. So we're talking about the higher brain. We're going to talk about the cerebellum and another number of other locations. Now, the first thing we're going to talk about is our primary motor cortex. So in our frontal lobe, this is what's giving us conscious control of our muscles, which then goes on to pyramidal pyramidal cells, Jesus, into the corticospinal tract, into the spinal cord, and then down eventually to our muscles. We have our basal ganglia, which is going to be deep inside of our cerebral cortex, which is going to help us maintain repetitive movements. So this is going to be walking, running, just maintaining your basic posture. So all of us have natural firing patterns. And that's the reason why if you watch different people walk, we all use very similar technique, but there's going to be a little bit of differences based upon weakness, strength, lack of mobility, hypermobility. All of those things are going to influence how we move. Now, over our parietal lobe, we have our sensory cortex where we're taking in all the information from touch. Occipital lobe on the backside is where we're processing our visual information. Temporal lobe is going to be important for our hearing. Now, deep inside, we have our diencephalon, and that's going to be made up of our amygdala, which is more the fear and threat detection portion of the brain, along with our hippocampus, which is about long-term memory. Our cerebellum is about coordinating and helping balance like high-level movements. Our midbrain is going to be with our thalamus, is going to be about processing information, and our hypothalamus is going to be really important for homeostasis throughout the body because it actively controls the pituitary gland. Then we have our pons and medulla oblongata, which is really important for things like just breathing and keeping you going even when you're being completely sedate. Yay. The things I just said, only now written out more. Now, talked about the brainstem. Now the reticular formation, this is going to be just that basic muscle tone of holding us in position and also basic cardiovascular respiratory function. Now we also have our analgesia system, which is going to be natural opioids, which we are producing for pain modulation from doing usually physical activity. In fact, I do not remember the exact amounts, but effectively if you run a 10 kilometers each day, so we're talking about like 6.2 miles, it actually has an equating amount to effectively how much morphine you'd be taking every single day for the same effect. And so it turns out this is also part of what's being more researched these days, which is our endocannabinoid systems and how those are important for pain modulation. Now, outside of the immediate parts of our brain, we have our sensory receptors. Our joint kinesthetic receptors are literally letting us know what the angle of our joint is. That's why if your hand or feet fall asleep, you're kind of like, where is this at? I no longer have that information. We also have what's known as a muscle spindle that detects stretch inside of the muscle. And when it detects that stretch, it tells the muscle to quit contracting so that it doesn't accidentally tear the tendon off of the bone. Or sorry, it detects stretch on the muscle through the muscle spindle. And whenever it is stretched, it tells the muscle to contract so the muscle doesn't overstretch and then tear. It is going to be the Golgi tendon organ, which is in the tendon that tells the muscle to quit contracting so you don't tear the tendon off the bone. The reason I care about this is because I have literally torn my pec off of the bone. And that was from doing weighted dips, and it was rep freaking 7. That's when pop goes the weasel and my pec was gone. Now, the reasoning for this is because I'm relatively strong and I was being cavalier. I didn't take a deload, blah, blah, blah. I'm getting older. And so what happened is my muscle spindles felt that stretch on the muscle. So muscle contracted. The Golgi tendon organs, however, did not fire. And so since it didn't fire, my muscles contracted obviously harder than my tendons could handle. And my tendon went pop goes the weasel. It feels like a thick magazine tearing and like also like a bungee cord snapping because you felt like a twang and like it rolled up. But first and foremost, it's just pain. Stuff happens. And yeah, I should have gotten reattached a lot sooner than I did, but hindsight's always 20/20. Now, a good example of how Golgi tendon organs work, and you won't get to watch this much in the wild these days because it turns out the rec center is relatively quiet, but have any of you guys recently seen somebody try to max out on a squat and you've seen them like take a couple shaky steps out, they start to sit down and then they effectively just like collapse and fall over like a slinky in the bottom? Anybody had that happen recently and they want to share? No? Okay. So what we have here is how our sympathetic nervous system. Okay, good, Zach. Oh yeah, yes, you're right, Tyler. You told us about Parker and him kind of overshooting his body's abilities. So our sympathetic nervous system is about getting us ready to fight or run away. So it's all about trying to get a lot of resources mobilized, getting our systems ready to go, and at the same time, effectively getting us to focus up. On the parasympathetic time, it's about trying to get us to relax and trying to get us to more actively recover from the stressors of our day. Now, take your time, go through it, but we're going to talk a little bit more about it later on. Now, we are always going to be processing this information that we're getting from our afferents through our central nervous system, which then in turn is going out to our efferents, allowing us to move. And it comes down to simply, we're going to receive a stimulus. This is going to then send the action potential to our nervous system. The nervous system is going to then make an interpretation, which is going to send out the response to our motor unit, and then our muscle is going to contract in response to it. And a really easy example of this, aside from your hand touches a hot pan and it pulls away before you even think about it, but how many of you guys have seen something falling and then reached out and caught it without even really having to think about it? Nice. So this integration can occur in a lot of different areas. And the hot pan, that's going to be the spinal cord. Now, when we're working our way all the way up into the cerebral cortex, that's going to be something like you guys are playing a sport, like you're playing baseball and you're having to make a judgment on what's going on with the way that ball is coming towards you. And is it fastball, curveball, changeup? How am I going to swing at it? Is it breaking in? Is it breaking out? Is it high or low in the zone? All of those informations require, or all that requires a lot higher thinking. The spinal cord, lower brainstem, and cerebellum, this is going to be a lot of the simple reflexes we naturally have when we're walking. Like you guys have probably found yourself slipping a little bit and your foot corrected rapidly because your nervous system is able to fire and fix these problems without having to go up to higher integration. Now, this is that part of that motor control. Now, as we move our way up, we can do more and more complex movements. And a reflex is going to be something we have where it is just a response we have of what we need to do. This is going to be a response over and over again, and this does not require any type of conscious awareness. So a good example of this is the natural desire to flinch when something comes at your eyes, because it turns out these are very sensitive little objects and you only got two of them. If you lose one, you lose depth perception. If you lose both, you're blind. So it's only natural that if something comes at your eyes really fast, it's not an extra massive barrier to protect you, but at least it's a bit of an eyelid. So it's natural that your eyes are going to shut and you're going to pull your head back to avoid getting that blow to your eyes. Now, I'm sure all of you guys have had that happen, may it be walking around, driving, or anything else where you saw something coming at you rapidly and you naturally flinch to avoid it. This is a reflex. Does that make sense to you guys? I realize I can't see the polling. Perfect, thank you guys. So we talked about the basics of how these muscle spindles and Golgi tendon organs work. The key is training is going to sensitize them and desensitize them appropriately. So by doing a lot of heavy resistance training and plyometric work, what you actually start to do is you make your muscle spindles more sensitive and you make your Golgi tendon organs less sensitive. And that's part of the confounding reason why I tore my pec off the bone. Because most of in your average sedentary person, your Golgi tendon organ is going to tell you to quit contracting your muscle, where you've only produced about, usually it's only about 1/3 of the force required to tear the tendon is working to tell you to calm down. Now, as through training, you get up to higher percentages until eventually you can accidentally go pop goes the weasel. Now, typically people that tear their tendons are usually doing very high speed work and they're relatively powerful in the first place, and or they're utilizing a lot of anabolic agents where their muscles are literally able to grow faster than their tendons are. Now, always keep in mind when it comes to muscle activation, we are going to be at the mercy of what's known as the size principle, which is where the bigger muscle fibers are going to be the last ones to be activated. So we start off selecting those smaller, slow twitch fibers, and then eventually work our way up to those bigger, more powerful, fast twitch fibers. And it's going to be the alpha motor neuron that carries the signal to a number of different individual fibers. So our slow twitch alpha motor neurons are going to maybe only recruit 10 to 100 slow twitch fibers. Our fast twitch big motor units might literally activate thousands of individual muscle fibers. So this is good because it allows us to have graded force production, and it allows us to be able to do fine-tuned movements with lower amounts of force with very great levels of control. So now we're going to go ahead and have you guys break into groups for the last little bit here. We are going to go ahead and talk ourselves a little bit about brain injuries, because we just talked about a lot of different structures in the brain, and I did gloss through them relatively quickly. So once we get you guys into the groups, that's who you guys are going to work with, and we're going to come back on Monday and have you guys go ahead and talk through effectively what's going on. Now, the way this is going to work is inside of your groups, we are going to have you have an athlete, and they have an injury to their brain in this region, okay? How would you expect them to present? Like, what would be going on with their ability to concentrate, their ability to move in a coordinated fashion, their ability to maintain their moods, their ability to deal with loud noises, their ability to deal with with bright lights, etc. So, do you guys have any questions there? Okay, I just put in the chat how I'm going to have each of those 4 groups structured. And in a moment, guys, I'm going to go ahead and have you randomly assorted into those breakout rooms. So make sure you guys are aware of what your group is going to be doing. And then you guys are going to go ahead and we're going to talk through this on Monday, along with we're going to go much more into the sympathetic nervous system. And I'm going to tell you some kind of fun stories about prefrontal cortexes and otherwise. So questions, comments, or concerns before we go ahead and I kick you guys into those rooms? Seeing as how there's none, go ahead, guys, get in the group, and you guys can go ahead and just kind of talk for the last few minutes of class. Otherwise, you guys are just you're welcome to go ahead and work on this outside of class, however you guys want to go ahead and approach it. So have fun, guys.